Here, let's take a look at the final type of the indeterminate problems I can summarize from the textbooks. And then this type basically feature is this. Here, the black area indicating is a solid. That means doesn't deform. So the loading applied to one material, red, this is deformed, and also this red will transmit the force to this one and to the solid, and in turn to press the green one that is deformed. So the feature of this type is this. The red one not only deformed, is both ends. This end and this end, both ends displaced. So this type will help us to introduce the concept of relative displacement. We see. So the problem statement is this, and assuming this shaft, okay, this shaft linking this and AB is deformable, and the two vertical is deformable. The only thing undeformed solid is this one. So when loading applied to AB, the AB deformed, then we can see the AB by looking at is the template. So this is the B here, this is A here. And so due to this kind of the solid at here, so here they have a P loading here. Okay, so assuming this is LAB, so the deformations in AB is PL over E and A for the AB cross section. For example, this is the cross sectional area. Let me call the AAB. Okay. Basically, this indicating is the deformation of the AB, and then here for notations, and I like to say this really indicating is also the displacement of B relative to A. Okay, so that basically indicating is the total deformations. Okay, so here let me relate it is in this. Okay, and for this case, basically this amount is PL over EA, and whatever the information we pick up about the rod AB. The substrate here I use is to indicate that the reaction and the force P, that is P. L, you take the information about the rod AB. E and A in the similar way, whatever the material properties and the geometry you pick out relative to AB. So that is the information here. And so here, because for this case, you can see the A is also displaced, and that in this case A will displace moving downward, and the amount is given by determined by how much the C this is downward. Okay, so here for these portions, for each side of the portion here, so say here this is C prime here. Okay, right now I pick up is a free bar diagram here. So let me take this is the L and say C prime. Okay, and the cross-sectional area is A, say C prime here, and the same thing, Young's modulus C prime corresponding to C prime here. So here, because through this rigid link, and there's a force transmitted, and that's P here, and due to action reaction, there's a P here. So from here we can determine the So from here we can determine the displacement. So this is the A, so that one basically shortened here. Okay, so this amount delta equal to PL over EA, and again you pick up information relative to the shaft C prime, L, C prime, E, C prime, A, C prime here. So that one deforming, and because this end is fixed, so basically this is a deformation simply replace is about is representing the displacement at A here. So if you want to determine this amount, basically that is PL over EA, and this is about the shaft C prime, and in the similar that is C. And again here I think I have made a mistake, and can you identify the mistake? The mistake is here. The P applied to here and that evenly distributed to the two sides. So here, rather than P, let's be equal to P over 2. Can you see? Because this one I pick is this free body diagram. So here, this one, rather than P, that should be P over 2. Okay, so that's a mistake I made here. So by doing so, in these sections, I simply introduce the B relative to A, this kind of new symbols indicating the deformation for this one. That basically is a relative displacement between B and A. That representing is the deformation of the shaft. Okay.